Then the question is asked, why do we need 0.7 volt voltage across the diode to send current through it? Actually, to send the current through it, diode should be forward biased. Then definitely we need forward bias 0.7 voltage across the diode. But we have to tell why it is required. Okay, here we have depletion layer. Then and we have positive charges here. And negative charges. The N-type region. Because of that, here we have potential barrier. Because of that, normally current doesn't go. Okay. To break this barrier, we need to apply some pressure from the ends. Okay. And to apply pressure, we can apply certain voltage here. Because of this arrangement, it's positive charges at the P-type N and negative charges at the N-type N will be appeared. Because of that, due to the same type of charges, appeared at the ends. Width of the depletion layer. It's decreasing. Okay. Okay, then we can break the depletion layer, but we need 0.7 volts if the material is silicon. Then half wave and full wave rectification methods of AC voltages. And this is the AC voltage we can give. And then through the diode, you know that only the positive half cycles can go to the other side. Okay. And you have to explain, you would write something when the positive half cycle is applied, the diode is forward biased, then through the diode, the voltage can go to the other side. When the negative half cycle is applied, the diode will be reverse biased, then no voltage can go to the other side. Then that voltage will not be appeared here. Okay, this is full wave, half wave rectification method. And then for full wave rectification, we need a diode bridge here. This is AC input. And we have waveform like this. Then during the positive half cycle, through diode D1, then through R, D1 and D3 diodes are forward bias. And D2 and D4 reverse bias. Then at the output, the positive half cycles are coming. And you can see the direction, the current direction to the resistor. Okay. When the negative half cycles come, then from this way, through D2, it can go, and then plus the resistor can come here. Now to come into this junction, it can go like this. So through the resistor, you can see that current is going the same direction. Because of that, the voltage will be appear the same direction during the negative half cycles. And during the negative half cycles, D2 and D4 diodes are mode bias, and D1 and D3 diodes are reverse bias. Okay. Here we haven't discussed about the smoothing, but you should know in addition to that one, then you should know about smoothing also. And when we put a capacitor, how this smoothing happens. Then we can include a reservoir capacitor in parallel to resistor R. Then with that we can smooth the output voltage. Okay. Then this is the Zener regulator. Okay, just you have to draw the Zener's regulator circuit, and after that we can find those two values. Because that you didn't have enough chance to, you didn't receive this tutorial first. That shall we spend a couple of minutes to understand the question and try it first before I discuss it? Sorry that I was muted that when I explained this one. And this is the Zener diode regulator circuit. And from this side, we have unregulated DC voltage, 15 volts. Then RS we have to calculate. And this Zener voltage is, it should be 8 volts. And we have to find this Zener current. And this input current. And the load current also. Okay. And this is the Zener regulator circuit. The next one is the maximum current flowing through the Zener diode. The maximum current flowing through the Zener diode. How can we find it? Because we know the Zener voltage. We said is 8 volts, and Zener voltage is how much? It's 1 watt. It's 1 watt. Then from this we can find the Zener current, the maximum Zener current. I said maximum current. Okay. Then 1 watt divided by 8 volts. Okay. Then this is 125 milliamperes. Okay, what is next? The maximum current flowing through the Zener diode is the minimum value of the series resistor RS. Okay, here this is okay. Then minimum value of series resistor RS. Then we know that we can write this equation. Then V supply equals V RS plus V Zener. Okay. From this equation we get, then V supply is how much it? 15 volts. VRS we don't know. And VZ is 8 volts. Then from this we get VRS is 7 volts. Okay. At that time, let's see. The maximum I set will be there when IL is 0. Okay. When the load current is 0, the current should bear by this Zener diode. That is the one. Okay. And here we have this relationship. IS equals IZ plus IL. During this time, IL is 0. Then we can take IS as IZ. Then we can calculate IS, because VRS we have to find RS. Then RS equals VRS divided by IZ max. This is RS minimum value. When the IZ current is having maximum value, then at that time we can find RS minimum value. Okay. And RS minimum is equal to VRS 7 volts. This is 125 milliampere. Then 7 divided by 125. Okay, then this is 56 ohms. Next one, the minimum value of the series resistor is the load current IL if a load resistor of 2K ohm is connected across the center diode. Okay. Now we are going to connect a load here. Across this one, load resistor, 2 kilo ohm resistor will be connected. Okay. Then if a load resistor is of 2 kilo ohm is connected across the center diode, then load current IL. We have to find load current IL. See. D. And here VRL is equal to VZ. This is 8 volts. Then we can find IL from this. This is VRL divided by RL. VRL is 8 volts. RL is 2 kilo. And this is this one, 4 milliamperes. Okay. Then the center current, if I is at full load. Full load, RL is 2 kilo ohm. Then when RL is 2 kilo ohm means that now we have IL as 4 milliampere. Then with this equation, IS equals IZ plus IL. IS, we know this is IZ because IS is 125 milliampere. That is maximum it's taking. IL is 4 milliampere. Then 121 milliampere current is going through the circuit when the load is at its full load. Is it okay? Then one question is asked that to explain the knee current for Zener diodes. Actually, Diniti, it's something like this, that we have this characteristic curve for Zener diodes. This one. This is the forward direction one, and here we can reverse bias the Zener diode, and this is the one. Okay, but actually, if we draw like this, okay, the actual one may be something like this. Small curvage is there. And here, if we take this one, it's something like this. Okay, it's not straight away bending like this. Then we take this one as we set Zener voltage. But there should be a linear region after this. Actually, we are considering this range to be used in the voltage stabilizer circuit, not this one. You can see that here voltage is changing and the current may be changed. But in this case, I have to draw this one a little bit straight, assuming that this may be considering this may be during this period. We have to find a linear region here. And during this region only, we can use this Zener diode as a regulator. Okay. And this is the Zener voltage, and this is the knee voltage we are having. Okay. This is the knee voltage we are having. At that time, when we have a current, that is knee current. But generally, we consider this knee current one is in a voltage somewhere here, and we can take that one as the starting point of the regulator circuit, Zener current. Let me try to find some figure from the web, then I can explain it. Yes. Yes, you can see this one. You can see this figure. It's taken from the web, and you can here see the Zener breakdown region. This is IZ minimum and IZ maximum. This is the region we can use for this Zener regulation region. Okay. Within this region, we can use this as regulator. Is it okay? What is the maximum current through the Zener diode when the knee current has been given? Actually, the knee current has been given means that within the Zener region, here in our example, you can see that the maximum current we can calculate through the Zener, that is 125 milliamp. But in this case, our load is 2 kilo ohm resistor, but Zener can go more than that. Now, when we have the maximum load, the load is taking 5 milliampere, the 4 milliampere current. Then Zener has to take the 121 milliampere current through it. But then we don't know that value, that assume that in this case, in our Zener, this may be the 125 milliampere one. And this, if we think that and if you take this one as 125 milliampere, and this may be, shall we take 10 milliampere? Then load can take 115 milliampere to load side. Within this region, Zener can operate as a regulator. But if the load is taking more than this, for example, here, this is Zener, I is set current. But during this time, what is IL? This is 115 milliamp. And here, what is IL? It's 0 milliamp. Okay. Then here, when Zener is taking maximum current, load current should be 0 milliamp. But beyond that, the Zener load current can be varied up to this 150 milliamp. Why? This is the minimum current we can see here. This 10 milliamp. We have assumed this one. Okay. But if the load is taking more than this, the 115 milliampere, if it's taking more than this, then the Zener cannot handle this. The Zener is going out of range. Then that regulation is not there. The voltage regulation is not there. Yes, I'll upload this tutorial after this. Okay. Shall we discuss this one? For transistor temperature, we have discussed this similar type of question yesterday also. VCC is 12 volts and R1 9K, R2 4K, then RC 1K, RF RE 1.8K and RL 1K. We have to draw the DC load line and determine the operating point. All the time that you have to remember this one, otherwise that you have to draw this one at the examination. Best thing is that you have, if it is possible to remember this equation, that is easy, okay? Then you know that IC equals 1 minus 1, then RC plus RE times VCE. Here VCC divided by RC plus RE. This is the equation. Okay, based on this equation, we can draw the load line. This is VCE. This is IC. Can I show the diagram when done? Which diagram? This one? Which one you are referring? Circuit, this one. This normal circuit that all the time you will receive this type of circuit. Okay, sometimes that it's here, it may be small difference. This one. You will have this input capacitor also. And this is P out, and this is C1, C2, and this is C2. This is the common diagram you will receive. In addition to that, we have this the fixed bias circuit. You may remember that there we don't have that this R2 resistor. We have only R1 resistor. But this is self-bias circuit. With the self-bias circuit, we have this R1, R2 resistor divider. Okay, then we can draw the load line. You know that load line should be something like this. Definitely you can draw this one. And you have to find these 2 points. Okay. When you find these 2 points, one thing is very easy. And we have to find this maximum voltage at this VCE bar. The VCE axis, you have to mark this one. This one happens when IC is 0. Then you can put IC is 0 like that. Then definitely this is the maximum value we can find. This is plus VCC. Because the circuit cannot go beyond that. Why? Here, this is the maximum voltage. Circuit cannot go beyond that. It has to, this is the maximum ceiling. It's the ceiling. We cannot go beyond that. Then because of that, this is 12 volts. Then we have to find this one. What is this one? This one comes when VCE is 0. Okay. When VCE is 0, then IC equals VCC divided by RC plus RE. Okay. Then here, this is VCC divided by RC plus RE. Okay. And this is the IC point when VC is 0, can receive IC equals VCC is 12 volts. What is RC plus RE? RC is 1K, RE 1.8K. 1K plus 1.8K. Then this is 12 divided by 2.8K milliamp. So that you have this K can be taken out. K is 10 to the power 3. Then when you take the 10 to the power 3 up, it is 10 to the power minus 3. 10 to the power minus 3 means it's milliamp. When you look at straight away K, that you can take it up and you can put milliamp. Then 12 divided by 2.8. 12 divided by 2.8 is 4.28. And we can take it as 4.29. 4.29 milliamperes. Then this is 4.29 milliamperes. Then we have to determine the operational point, Q point. How can we determine that one? Then we have to come from this side. When we have this voltage divider, we have to calculate this point voltage, that is VB. With that VB, you have to find current going through this path. Okay. Can you try this one? The next step. Okay, then with this R1 and R2 values, what is R1 and R2? R1 9K, R2 4K. R1 9K, This one, this is 4K. Then we can find this point voltage, that is VB. Okay. Then VB is 4K times VCC divided by 9K plus 4K. And this is 4. VCC is 12 volts. Yes. This is 12. Then 9 plus 4, 30. This is 3.69 volts. Okay. VB is 3.69 volts. Then we can write equation. Then this equation we can write VB equals VBE plus IE RB. Actually, what we are looking for, this one. Why do we find these things? We have to find this current. Which current? We have to find this current. This IB current. Okay. Sorry, not IB. We are not going to find this IB. We are going to find this current, this IE current. Why? Now, when we set the operational point, we have to find IC. At the operational point, we have to find this IC current. This IC current. To find IC, there is no other way because we don't know these values. Okay. We don't know, then somehow we have to come to this side. Then we know VB, why this resistor divider network is here. Because of that, we can calculate VB. When we know VB, this is 0.7 volts. Then we know VB, we know this one. Then we can find VRE. When we know VRE, we can find IE. Because we know RE. Okay. Then here with this equation, we can find IE VB minus VBE divided by RE. This is VB is 3.69 minus 0.7. This RE, how much? RE 1.8K. 1.8K. Then you know that when we have K, you can take it up, then that is milliampere. then 3.69 minus 0.7 divided by 1.8. This is 1.66 milliamp. Now that is the one parameter we need. Okay. Then we know that we can write like this, then because IC is equal to IE. Why? Because IB is very small compared to IC. With that approximation, we can write equation for this part, plus VCC equals IC RC plus VCE, then IC RE. Okay. Then we can find this VCE to VCC minus IC RC plus R. This is 12 volts minus IC. IC is 1.66 milliampere. RC, how much? RC 1K. RC 1K, and this is 1.8K. Okay. 12 volts minus 1.66 milliampere, 2.8 K. We can cut this milliampere and K here. Then 12 minus 1.66 into 2.8. Then 4.65. Okay. Then this is 7.35 volts. This is the other value we need. This is VCE value, and this is IC value. Okay, then we can mark this one there, 1.66 milliampere, and this is the Q point. Here, this is 1.66 milliampere. And the current is 1.66 milliampere. This then this voltage is 7.35 volts. 7.35 volts. Okay. I think now you have enough experience to find this one. The next circuit in the transistor amplifier shown above, the same circuit you have to use. RC is 10K, RL is 30K, and VCC 20 volts. But here